In the last lecture, we introduced the idea of flux and then stated Gauss theorem, which says that the flux through a closed surface is equal to the charge inside the surface divided by epsilon 0. We also found the electric field due to a non-conducting spherical charge, non-conducting sphere which is charged uniformly. And now, we find potential due to a non-conducting uniformly charged sphere. And how do we do that? Recall the relation between the electric field and the potential. Electric field is equal to minus d phi by dr. Therefore, phi is E times dr and the integral of that would give us phi. So, phi is minus integral of E dot dr. Then it follows from E, for a point outside the sphere, you remember E was given by this, and the potential outside the sphere therefore, is E times dr integral of that, and this gives us a cubed rho 3 epsilon 0 into 1 by r. You see, E dr becomes integral of E dr becomes, you can integrate that, and 1 by r squared will give you minus 1 by r, minus gets cancelled with this, and you get phi outside equal to a cubed rho by 3 epsilon 0 into 1 by r. So, that is the potential outside for a point outside. Remember, for a point outside, the sphere acts as a point charge at the center of the sphere, and this vanishes at infinity. We know that on the surface of the sphere, if I put r equal to a, phi surface is a cubed rho 3 epsilon 0 into 1 by a. So, it is a squared by 3 epsilon 0. If I substitute the value of rho, I will get q by 4 pi epsilon 0 a. So, you know already this in fact that for at a point distance a from the center of the sphere, the potential is given by q by 4 pi epsilon 0 times a. For inside the sphere, again we have the same strategy, E dot dr. So, we substitute the value of E and then we carry out the integral E dot dr, and we use a constant c to match the potential inside and at the surface, so that there is no discontinuity. Therefore, we find that if we carry out the integral E dot E dr, then we find that, remember, E is rho by 3 epsilon 0 times r, we found in the last lecture. So, therefore, phi inside is, if I substitute the value here, minus rho by 3 epsilon 0 r squared by 2 dr is r squared by 2 plus a constant c. And now, we match the two, phi inside and phi at the surface, and if we match the two, then what happens? Then c, the c constant, we get equal to this. So, we substitute it back into this equation and we get phi inside equal to rho by 6 epsilon 0 a squared minus r squared plus q by this. So, that is the potential inside, and you can verify this is correct. If a is equal to r, that is, we are at the surface, this vanishes and we get the value at the surface. So, this there is no discontinuity and the phi inside just matches with the phi at the surface, and we recover the value. At r equal to 0, we again recover the value of the potential at the center, which is, if I put r equal to 0, this is equal to 3 by 2 q 4 pi epsilon 0 a, which is 3 by 2 times the value at the surface. So, this continuity of the potential inside and the potential at the surface gives us the potential at the center if I put r equal to 0, and this is 3 by 2 times the potential at the surface. So, therefore, if I plot, then the at r equal to 0 at the center of the sphere, the potential is 3 by 2 times, this is the potential at the surface. So, 3 by 2, that is 1.5 times the potential at the surface, and then outside, from the surface outside, it varies as 1 by r. So, that is the profile of the potential due to a non-conducting sphere which is uniformly charged. Let us now take a charged conducting sphere, and the first thing to note is that a conductor has a constant potential all over. It is the equipotential surface, because if there is a difference of potential, that would mean an electric field that would apply force on charges, and the charges will move, they will not remain static. Therefore, there cannot be any potential difference between 2 points on the surface of a conductor. So, the conductor is an equipotential surface. The constant value of the potential will have to be the same as that at the surface for continuity. Otherwise, there will be potential difference, and unwanted electric fields again will create problems for us. So, it is easy to show by drawing Gaussian sphere outside the conducting sphere. We see, remember the same thing, we have a sphere which is uniformly charged, but the charge now is on the surface and is a conducting surface, and we draw a sphere outside this Gaussian sphere outside this. For points exterior to the sphere behaves as if the whole charge resides at the center of the sphere. If the charge carried by the sphere is q, the charge at any point at a distance r from the center is given by the field at any point is given by 1 by 4 pi epsilon 0 q by r squared. The charge behaves, the sphere behaves as if the whole charge resides at the center of the sphere. So, the field is q by r squared into 1 by 4 pi epsilon 0. The charge on the sphere has been assumed positive, and that is why we have this r cap going outside. If it is a negative, then the field direction is reversed. For points interior to the conducting sphere, we draw now a Gaussian sphere inside of radius capital R. The charge is outside, and the charge in a conductor resides only at the surface. Inside there is no charge. So, we want to find out the field inside. So, we draw a Gaussian sphere inside of radius capital R, and we note first that the constant potential inside means that the electric field vanishes. If there is a constant potential, electric field vanishes. If the electric field vanishes, then E dot ds vanishes. If this vanishes, then E is 0. If E is 0, then q by epsilon 0 is also 0, which means q is 0. That means there is no charge inside a conducting sphere, there is no charge inside. All the charge just migrates to the surface. All the charge has migrated to the surface, no charge can reside inside the conducting sphere. In fact, you take any conducting surface, the charge will be only on the surface, no charge inside, because if you draw a Gaussian sphere inside, because of constant potential, the electric field will be 0, which implies that q is equal to 0. So, let me show you now the profile of the electric field due to a charged conducting sphere and the potential due to the charged conducting sphere. We have found that the electric field inside this conducting sphere must be 0. So, E is equal to 0 up to the surface. At the surface, it has a value, and then it decreases as 1 by r squared. Because E is equal to 0, the potential inside is constant, and this constant potential has the value, the same value as at the surface of the sphere, and from that point outside the sphere it varies as 1 by r. The potential varies as 1 by r, inside the potential is constant. The electric field inside is 0, and from the surface outwards it varies as 1 by r squared. Let us now take a uniformly charged thin spherical shell. We had a uniformly charged sphere, now we have uniformly charged thin spherical shell. Shell is a sphere which is very small thickness, inside it is empty. If sigma is the surface density of the charge per unit area on the shell of radius a, then the charge on it is 4 pi a squared sigma. 4 pi a squared is the area of the sphere, sigma is the charge density, that is charge per unit area. Therefore, the total charge on the sphere is 4 pi a squared sigma. So, without going into any details, you can see as before, for points outside the sphere at a distance r from the center of the shell, the field will be as due to the total charge placed at the center of the shell. Formally also we will now show. We draw a spherical Gaussian surface at radius r outside, the point P is at a distance r from the center. This is the shell and this is the Gaussian surface, and since Gaussian surface is a sphere, the field by symmetry must be radial to it, that is normal at each point on the surface. Therefore, the flux is 4 pi r squared E, which is equal to q by epsilon 0. Q is the charge inside this Gaussian surface, and what is the charge inside? The charge inside is the charge on the shell, which is 4 pi a squared sigma. So, we get the field E equal to a squared sigma by epsilon 0 into 1 by r squared. If we equate these two, we will get the field, and we can, this q has been expressed in terms of sigma. So, it is a squared sigma by epsilon 0 into 1 by r squared. So, the charge has been assumed as positive. Therefore, the field is outside, otherwise the direction of the field is reversed. At the surface of the shell, the electric field has the value, when r becomes a, that is the surface of the sphere, the value is simply sigma by epsilon 0. For points on the surface and outside the shell, the field varies as 1 by r squared, as if the charge is concentrated at the center of the sphere. This we have been seeing time and again. As far as the points outside are concerned, the whole charge is concentrated at the center. Now, for a point inside the shell, we draw the Gaussian surface inside the shell, but there is no charge inside this Gaussian sphere, because it is inside. We have drawn the surface inside the shell, the charge resides on the shell. Therefore, inside this Gaussian surface there is no charge. So, 4 pi r squared epsilon 4 pi r squared E would be equal to 0. 4 pi r squared E, where r is the radius of this Gaussian surface drawn inside the shell. So, 4 pi r squared E is equal to 0, because there is no charge. So, q by epsilon is 0, therefore, this is 0, and therefore, this gives E inside, which is equal to 0. So, inside the shell electric field is 0, outside the shell it goes as 1 by r squared as usual. So, I again show the electric field inside and outside a charged spherical shell. Inside the shell the field is 0, outside it goes as 1 by r squared. It is easy to work out the electric potential. Again, remember the definition, minus d phi by dr equal to E. So, if you remember that, you can get the potential at various points. For r equal to a, it is a sigma by epsilon 0. For r greater than a, it is a squared sigma by epsilon 0 into 1 by r, because the charge behaves as if it is concentrated at the center. So, it is 1 by r. And for r less than a, since E is 0, the potential must have a constant value, and this value has to be equal to the value at the surface. So, that there is no discontinuity. So, again I will show you the profile. You see, up to a, from the center to the surface, the potential is constant. It has the same value as at the surface, and then from that outside the sphere or shell it varies as 1 by r. We now take a line charge. Line charge is nothing but a long line or a long conductor, say thin wire carrying charge, which is uniformly distributed over the line. Symmetry dictates that away from the ends of the line the electric field will be radial, because if it is any other direction, that will have a component along the line and will exert forces on the charges, will move them and so on. Therefore, there cannot be any component along the line. So, the electric field has to be normal to the line. Suppose we wish to find the electric field at the point P at a distance r from the line, at a point P at a distance r from the line. So, what we do? We draw a Gaussian surface. In this case, the Gaussian surface is a cylinder of radius r. Now, the electric field is parallel to these plane sides of the cylinder. Therefore, there is no flux through them. The only flux through the cylinder is through the curved surface. Remember this as we go along. And what is the surface area of this cylinder? The curved surface, it is 2 pi r times L. L is the length of the cylinder. So, the flux therefore is 2 pi r L times E, because E is normal to the line. So, therefore, the angle theta is equal to 0 and cos theta is 1. Therefore, phi E is 2 pi r L times E, where L is the length of the cylinder. The charge inside the cylinder is Q equal to L lambda. Lambda is the charge per unit length, and if L is the length inside the cylinder, or L is the length of the cylinder, then the charge inside the cylinder is L times the charge per unit length. So, it is L times lambda. So, charge is L times lambda. Now, we apply Gauss theorem. Gauss theorem says that the flux must be equal to q by epsilon 0. So, we substitute the values and we get E equal to lambda by 2 pi epsilon 0 times r. That means, the field varies as 1 by r from the line charge. We are accustomed to field varying as 1 by r squared, but now because of this symmetry, this line charge, field is always normal to the line, and if we apply Gauss theorem, then we find that the electric field is lambda by 2 pi epsilon 0 r, where r is the distance from the line, and what is important is that the field varies as 1 by r and not 1 by r squared. Lambda is the charge per unit length, and moreover that the field depends only on the charge per unit length and not the length of the line charge. So, it is simply proportional to lambda. So, lambda is constant, therefore, this field varies as charge divided by r. For potential, we remember that minus d phi by dr is equal to E. So, if we use that formula, then we get phi is equal to minus lambda by 2 pi epsilon 0 log r, log to the base E. Why? Because the integral of 1 by r is log r. So, therefore, the potential is minus lambda by 2 pi epsilon 0 log r, and you can verify that if I have this phi, then minus d phi by dr gives me the field lambda by 2 pi epsilon 0 times r. You see, these little consistencies are always better for checking the results. There should be no, physics does not brook any inconsistency. You must be consistent always. Now, we take infinitely large sheet of uniform charge density. So, we have a sheet, very thin surface sheet, which is infinite in size, and there is a charge on it which has a constant density, say sigma. So, we want to find the field due to this sheet of charge. So, what we do? We now erect a Gaussian surface on this sheet, and what is this Gaussian surface? Gaussian surface is a cylinder, and however thin the sheet may be, it has two surfaces, one and the other sheet, one here, one here. So, therefore, this cylinder encloses the sheet, the surface on this side and the surface on the other side. And the flux, what is the flux? Flux is only through these plane sides, not through the curved sides, because the electric field is parallel to the curved sides. So, the flux through these plane sides is from this side as well as from the other side, because the sheet has two sides. Therefore, the flux is 2 times E A, which is equal to sigma A by epsilon 0. The flux through the two plane surfaces is 2 E A, E is normal, therefore, E times the area, and the charge on area A is sigma A q by epsilon 0. So, we will have 2 E A equal to sigma A by epsilon 0. That is the Gauss theorem, and from this we find field. Field is sigma by 2 epsilon 0. It is independent of the surface area of this Gaussian surface. Notice that the field is independent of the distance of the point P from the sheet. That is important. You see, as long as the distance is not very large from the sheet, the electric field at any point outside the sheet is independent of the distance from the sheet. That is important, and this fact you remember is very important. This we shall make use when we draw the expression for the parallel plate capacitor. This is because the sheet is infinitely large. However, infinitely large sheet is an idealization. You can't have an infinitely large sheet. In real life, the result is valid as long as we are away from the edges of the sheet. So, we have a large sheet and we are away from the edges. As long as we do that, we are fine, there is no problem. So, instead of a sheet, now we have a charged conducting plate. Plate has, there is a conducting plate, therefore, all the charge has migrated to the surface of the plate. That is one thing, and this is equivalent to 2 sheets, and therefore, the field will be twice. It was sigma by 2 epsilon 0 for the sheet. For the plate, it will be twice that, because now there are two charged surfaces. The whole charge has gone to the surfaces. So, we have charge on this surface as well as the charge on this surface. So, the field is twice, but formally you can draw a cylinder which is inside the plate, but not crossing the plate. So, the flux will be only through this surface, not two surfaces, but to only through this surface, and if you apply now Gauss theorem, you will get the result as E is equal to sigma by epsilon 0. We can embed the Gaussian surface in the conductor, since there is no field inside the conductor, no flux crosses the plane side embedded in the conductor. As I have been telling you, through this side there is no flux, because there is no charge inside. The only flux is through this. So, now if you apply Gauss theorem, you will have E A equal to q by epsilon 0, q is a sigma. So, therefore, E is equal to sigma by epsilon 0. If we have parallel sheets of charge, say positive sheet and then negative sheet, then what will happen? Positive sheet, this is positive sheet, it has field going away from it on both sides, but if we consider point inside these two sheets, then the field of the positive charge is pointing upwards. The field of the negative charge is also pointing upwards, is it pointing towards the sheet. It is away from the sheet for the positive charge, it is towards the sheet for the negative charge. So, both the fields are actually in the same direction, and the field due to this is, they are added, the field due to this is sigma by 2 epsilon 0, the field due to this magnitude is also sigma by 2 epsilon 0, you add them up and you get the field inside at point P. So, as long as we are inside the two sheets, we have the field equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0, because both are added, and therefore, the total field has a magnitude sigma by epsilon 0, again independent of r. As long as r is not very large, as long as we are inside the two sheets, the field is sigma by epsilon 0. So, as I have said, the field reinforce each other. This is away from the sheet, positive charge, negative charge towards the sheet. So, the inside the electric field is all in the same direction, and the vector sum is just the addition. Same thing happens if the upper sheet is positive and the lower sheet is negative, does not matter. The field has a magnitude sigma by epsilon 0 inside these two sheets. So, in this lecture we have seen several applications of Gauss theorem. The most important thing to remember is that the Gauss theorem uses only the charge inside the surface, one thing. Second, for points outside the surface, the charge on whatever surface is there behaves as if it is concentrated at the center of the surface, and therefore, for outside the field is always 1 by r squared, q by r squared, and the charge is concentrated at the center of the sphere. Whatever the sphere, whether it is non-conducting, conducting, whatever. The other thing we saw was the application of Gauss theorem to a line charge, and more importantly to a sheet of charge, because this application to sheet of charge we shall use later on when we find the capacity of a parallel plate capacitor. In the next lecture, we shall consider again applications of Gauss theorem to certain problems, so that the ideas of Gauss theorem get fixed, that is, that the flux through a surface is equal to q by epsilon 0. The integral of E dot ds is q by epsilon 0. Repeatedly we shall use this result to several problems, so that this concept is clarified.